Okie dokie, so for some reason my videos got messed up, so I'm going to do 9.1 and 9.2 and probably 9.3 in a different way. So I'm going to use my document camera. Move my microphone to a good spot. There we go. Alright, so discussion 9.1 is all about solutions and concentration. So we're going to talk about how we make a solution, how we can vary the concentration, how we express concentration, and we'll talk about what happens to concentration when we dilute. Okay, so first, what is a solution? A solution is just another name or another word for a homogeneous mixture. So please recall that a homogeneous mixture is one where two substances are mixed together and you have a uniform composition. So a lot of times they'll be clear. Solutions could be colored, but they'll be clear to see from, and they won't settle out over time. So a solution forms when two substances are mixed together and one dissolves in another. So one substance dissolves in another. Now, there's a number of different factors that can affect the rate of dissolving, how fast something dissolves. One is temperature. Right? If you try to dissolve sugar in tea, if the tea is cold, it will not dissolve nearly as fast as if the tea is hot. Another factor is surface area. Back in the day, people used to use sugar cubes. If you had a sugar cube versus powdered or granulated sugar, you'd see that the granulated sugar would dissolve in water much faster. And the third is polarity. Now remember the rule, like dissolves like. And what we mean by like dissolves like is that polar substances will only dissolve in other polar substances. And nonpolar substances will only dissolve in other nonpolar substances. And that's the reason why, for instance, oil and water don't mix in Italian dressing. Because oil is nonpolar and water is polar. Because they have different polarities, the two things will not mix together. All right, so let's cover some vocabulary. Solute, there's really two definitions for this. A solute is the thing being dissolved. So if we're dissolving sugar or salt in water, the sugar or salt would be considered the solute. Now the other definition is it also could be the minority component. In other words, the component of the mixture that you have less of. And the solvent is the substance or the thing that is doing the dissolving. Also could be considered the majority component. So if you have salt water, we're dissolving salt in water, so the solute would be the salt and the solvent would be water. Now we use these alternate definitions when it's kind of difficult to decide what is being dissolved in what. For instance, air is a homogeneous mixture of several different gases. It's about 80% nitrogen, about 18% oxygen, and the rest is carbon dioxide, argon, and some other components. Since nitrogen is the majority component making up 80% of the atmosphere, we can say that nitrogen is the solvent and all the other gases are solutes. And soluble just means can be dissolved in a particular substance. So salt is soluble in water because it will dissolve. And insoluble means cannot be dissolved in a particular substance or solvent. So oil is insoluble in water. All right, so solubility. We can actually quantify solubility as the amount of solute that will dissolve in a particular amount of solvent. Each solvent can only hold so much solute. And the more solute you can fit in a given amount of solvent, the more soluble that substance will be. So that brings us to unsaturated, saturated, and supersaturated solutions. Now, an unsaturated solution means a solution is not full. It can hold more solute. And so if you had a beaker of water and you took some table salt and threw it in, you would see that salt dissolve. So it would disappear and the solution would be mostly clear. Now, in a saturated solution, we're talking about a solution that is full of solute. It cannot hold any more solute. So if we have a saturated solution, let's say we take the solution we had here and continue to add salt to it, eventually that solution is going to be saturated. And when it's saturated, the salt will no longer dissolve, and so it'll collect in a pile on the bottom of the beaker. And supersaturated solutions occur when we take a saturated solution and heat it. So there's a candle or a Bunsen burner underneath. We heat it. Now, when we heat that saturated solution, it will be able to hold more solute. Once we cool it down, that solute will stay dissolved, but it's a very unstable mixture, and so a slight change can cause it to come out of solution. So a supersaturated solution, I guess you could say, is kind of an overfull solution. It has more solute than it usually could at a given temperature. All right, so this is a solubility curve. A solubility curve gives us the solubilities of different compounds, and the units of the solubility in this curve are the number of grams of solute we can fit for every 100 grams of water. So each line represents the solubility of a different compound over the temperature. So as we're changing the temperature, we're seeing changes in the solubility of these compounds. So questions you might see is, what happens to the solubility of sodium nitrate as we increase temperature? Okay, stop texting me. All right, so we see that the solubility of sodium nitrate increases as temperature increases, so we could say that it increases. Also, we could give you a particular temperature and say how much sodium nitrate will dissolve in 100 grams of water at 40 degrees Celsius. If we do that, we trace up to the line. You see it's right about in between 100 and 110, so I would say about 105 grams. All right, next, how do we represent concentration? So concentration is represented with something called molarity. And molarity is the number of moles of solute divided by the volume of solution in liters. So if we simplify this, molarity becomes a capital M, and molarity will equal the number of moles of solute divided by the volume of the solution. So when we calculate molarity, the unit on top will always be moles, and the unit on volume will be liters. So the unit will be moles per liter. Now you can also simplify this unit into a capital M, and capital M means molar. So if I tell you that I have a 3.0 molar solution of HCl, that means there's 3 moles of HCl for every 1 liter of solution, moles per liter. Okay, so let's look at some molarity problems. Now, oftentimes you'll be given a very simple problem where you're given the number of moles and the number of liters. As long as you know the formula, molarity equals moles divided by volume, then you will know that you just have to plug in the numbers and solve. Sometimes, though, you might be given amounts in volumes of milliliters, or you might be given amounts in grams. If that's the case, you have to make the conversions to moles or liters before you begin. All right, so this first problem tells us we have 0.060 moles of NaCl in 1.5 liters of solution. When I put that into my calculator, I get that my concentration is 0.040 molar. I can just use that capital M. You'd be just as correct if you use the unit moles per liter, but you're going to see this one a lot more. All right, the next example says, what is the molarity of 250 milliliters of a solution containing 1.55 grams of KBr? Well, again, if it's asking us for molarity, we need to use this formula. So I have to get my amount in moles, and I have to get my volume in milliliters. So let's look at the number of moles first. It tells us that we have 1.55 grams of KBr. Now, ordinarily, if you want to convert grams to moles, you need your periodic table. Remember that G stands for get your periodic table. But in this problem, we're given the molar mass. So we have 119 grams of KBr for every 1 mole of KBr. So when we plug in and solve, that gives me 0.0130 moles. Next, I have a volume in milliliters. If we want to convert milliliters into liters, we have to divide the amount of milliliters by 1,000. So when we do that, a quick way to do that is to just take the decimal point and move it 3 places to the left. So our decimal point is now there. So our volume is 0.250 liters. Now that we have our numbers, we can plug into our formula. I have 0.0130 moles divided by 0.250 liters. And I get that my concentration is 0.0520 molar. Okay, next, preparing a solution. So we can use this formula for molarity in a bunch of different ways. Like we just saw, we could use it to calculate the concentration of a solution. If we're given a volume and a concentration, we can also calculate the number of moles of solute needed. So if we needed to prepare a solution with a given concentration, that's exactly what we would do. We'd have to determine how much solute we would need to add per liter of water to make the solution. All right, so the first thing we're going to do is weigh out the number of grams of this salt that we would need. Now it tells us we want 0.1 liters of a 0.1 molar solution. So using our molarity formula, we can calculate the number of moles that we would need to make that solution. So our molarity is 0.1. That's going to equal the number of moles divided by the volume, which is 0.1 liters. And when we do that, we get that there's 0.01 moles of solute needed. So now that we have the moles of solute, you got to remember our balances in the classroom do not measure moles, they measure grams. So we're going to have to convert that into grams. So again, I'm given the molar mass. So now I'll put 1 mole down here so that moles will cancel. I'll put the molar mass up here. And when we I get that that's 1.70 grams of solute. So I'm going to go over to my electronic balance. I'm going to weigh out 1.70 grams of the substance. I'm then going to dissolve that solid in a beaker with some distilled water. Now I'm not going to fill up all the way to 0.1 liters. I just want to get that substance dissolved. Now the reason we do it in a beaker is because it's easier to just stir it around in the beaker. Once it's dissolved, we'll pour the solution into a graduated cylinder and fill that graduated cylinder to 0.1 liters to get the desired volume. All right, dilution. So dilution is when we basically add more solvent to a solution. Usually that solvent is going to be water. You know, if your Kool-Aid is too thick and sweet, you're going to dilute it by adding water. All right, so what happens to concentration when we dilute a solution? Well, obviously, let's look at our formula. I like to do everything as mathematically as possible. Right? If all we're changing is the volume, then we're making the denominator of that expression bigger. Right? If we make the denominator of that expression bigger, it's going to make our output, the molarity, smaller. So the concentration will decrease as we dilute. Now, when we dilute, we're adding additional solvent, so the amount of solvent will increase. Now the key here, what happens to the number of moles when we dilute a solution? Well, the number of moles remains the same. All we're doing is adding more solvent. We're not doing anything to the amount of solute. So we can say that the number of moles of the undiluted solution will be equal to the number of moles in the diluted solution. So if you rearrange this equation to solve for moles, you see that mass times volume is equal to moles. So if moles equals moles, we can say m times v equals m times v. Only we have our initial conditions before we dilute, so we'll call that m1 and v1, and our final conditions after we dilute, which we'll call m2 and v2. So this is our dilution formula. This is another formula you got to know. All right, so let's do a little practice. I want you guys to do this by pausing the video and coming back to it to see what you get. Okay, so hopefully you've paused your video. It says, calculate the molarity of 0.289 moles of KBr in 1.5 liters of solution. So it's asking us for molarity, so we need capital M equals moles over volume. I'm given 0.289 moles and 1.5 liters of solution. The numbers are already good to go. We don't have to do anything to them. So 0.298 divided by 1.5. My calculator is equal to 0.1986666. So to round this to significant figures is going to be 0.20 molar. All right, next example says, what volume? So just those words, what volume, make me think that I'm going to have volume as my value for X. Of 4.5 molar copper 2 chloride stock solution would you use to make 0.5 liters of 3 molar copper 2 chloride solution? So the main problem a lot of kids have is determining what numbers go together. You just have to read the problem very carefully. It's telling us we're making 0.5 liters of a 3 molar solution. So obviously these two numbers go together. Now because this is an equation, it doesn't matter which side of the equation you put the numbers on as long as you keep them together. So I'm given a volume, I'm given a concentration, I'm asked for a volume, and I'm given a concentration. So we got 2 V's and 2 M's. So we know we're going to be using M1V1 equals M2V2. So our value for X will be V1, and the concentration of the undiluted solution is 4.5. So we're going to have 4.5 times X equals 0.50 times 3.00. And I get that the value for X is 0.33 on and on. And we're looking for a volume, so that's going to be 0.33 liters. Well, if you know the formula and are able to read the problem and understand, it's really not that hard. Finally, colligative properties. Colligative properties are properties that can change, or properties that do change, as a solute is added to a solvent. Properties that change as a solute is added to a solvent. Now, colligative properties will always depend on the number of solute particles that you add. So if you add more solute particles, you'll have a greater effect. So let's look at 3 different colligative properties: boiling point, freezing point, and vapor pressure. So if you add salt to water, you'll see that its boiling point increases. Now, the reason that the boiling point increases has everything to do with intermolecular forces. So boiling is the separation of molecules, taking them from the liquid phase to the gas phase. So when we separate those molecules, we have to break the intermolecular forces. And the intermolecular forces arise from positive and negative charges being attracted to each other. When you add salt to water, you're increasing the total amount of positive and negative charges inside, so you're actually increasing the total intermolecular force, and so you have to put more energy into the water to make it boil. Now, freezing point actually decreases as solute is added, and it decreases because of the nature of freezing water. When water molecules freeze, they line up next to each other and lock into an orderly pattern. They form nice hexagonal rings that are hollow in the center, and that's actually why ice is less dense than liquid water. But when they freeze, they must line up in this way. Now, when you have a whole bunch of ions floating in the water, the ions actually get in the way of the water molecules connecting up in this way, and so the water molecules have to be chilled even further in order to cool them. We see this colligative property being used all the time because they put salt on icy roads. They do that to lower the melting point of the ice so that it will melt at a colder temperature than it usually does. Finally, vapor pressure. Well, you have to remember that vapor pressure is intricately linked with boiling point. So as the boiling point increases, the amount of evaporation you're going to get will also increase. Now, vapor pressure is caused by evaporation, and the more evaporation you get, the higher the vapor pressure. So if increased boiling point means decreased evaporation, then it also means decreased vapor pressure. All right, now that is it for this discussion. Please bring any questions you have to class. Make sure you study hard for the quest we're going to have on this. If you know the formulas and understand the concepts, it's really not that bad. All right, thanks again for watching. Have a good one.